have our heats of formation. Actually, this is, yeah, heats of formation for this one. So you're given 2 equations, 3 equations. Usually for heats of formation, they'll say, here's what I want you to get. And this is kind of the same for the Hess's law. Here's what I want you to get. It's your target equation. And then you have a table that's heats of formation of various items. So you would find the heats of formation that you could rearrange to get your target equation. So in this case, I want to get from diamond to graphite. I have no idea why you'd want to undo a diamond, but they do. So I have diamond plus O2 gives me CO2, and that has a delta H of negative 395. And then I have graphite plus O2 gives me CO2, and it has negative 393. Well, I want graphite on my product side, so what am I going to do? I'm going to flip this equation. So this whole side is going to go over here, and that's now going to be over there. Because once I do that, if I rewrite it, I'll have CO2 and when I flip an equation, I have to flip the sign on this. So now it's going to be delta H equals positive 393.5. I can cross out my carbon dioxides, which is great because they're not in my final equation, are they? So they have to cancel. And then all I'm left with is the graphite on the product side and the diamond on the reactant side. And then you can just add these down. So positive 393.5 plus negative 395.4 gives me a delta H of negative 1.9. Yes?
What is this from?
This is either Hess's law or heats of formation. But it's all finding the delta H of a reaction. There's just 3 different ways we do it, yes.
So that you cross off your O2 and that carbon's just magically a diamond? Why is it graphite?
I'm sorry, both, yeah, these will cross.
So
That'll cross out too.
why is that carbon not graphite? Does a carbon have a choice?
There's more to this equation. It's like insane pressure and things like that.
So for our purposes, it's just that.
For our purposes, it's just an equation. Just an equation. All right, Hess's law. So that was heats of formation. Hess's law just takes it one step farther. It's still trying to figure out the same thing. So Hess's law says, for example, suppose you're given the following data. We have solid sulfur plus O2 gives us SO2 gas for a delta H of negative 297. And we have 2SO3 gas gives us 2SO2 plus O2, and that delta H is positive 198. Can we use this data to find the delta H or the enthalpy change for this target reaction? So this is the reaction they care about. 2S solid plus 3O2 gives us 2SO3. So why don't you go ahead and see if you can figure that out, and I'm going to try to block this one. So it's like the one we looked at on the previous slide. should end up looking something like this. So to make everything cancel, we have to have the coefficients cancel out too, if we don't want. So if we have 2 on one equation, let's say O2, and 1 in the next equation, but we don't have any O2 in our final equation, we have to multiply that second one by 2 to get rid of it, or the top one by half, whichever makes your problem work out. So in this case, they multiply the first equation by 2, and then flip the second equation, and when they cross out the ones that are on each side of the equation, you have to do the same thing. Whatever you do to the equation, you have to do the delta H, and then add it up, and that should give you the final enthalpy.
So for this one, we had to use both of the examples.
Yep. Because each one had part of what you needed in the equation. Yes.
So when you add like the top equation and the bottom equation, and like the 2O2 and the 1O2, they add, and that's how you get the 3O2 at the bottom.
Yep. If you don't cancel it out, it adds. Alright, now activation energy, we need to remember that to calculate our delta H, the activation energy, right? Minus activation energy left.
Is that bonds broken, bonds formed?
No. It's activation energy. So, we were given tables, remember, and you had to fill in the missing parts. You were either given delta H and activation energy going right, or activation energy going left. You have to fill it into this equation to figure out the missing piece. So if I said if EAR equals 30 and EAL equals 50, what is delta H? So you should be able to figure that out with this equation. Then EAR, remember that's the activation energy, which is where the products are, or sorry, where the reactants are, to the top of this peak, where we have our activated complex. So going right, that's where our activation energy, it's the difference between here and here. Now going left, it's going to be the difference between where the products end and the top of this peak. Everything goes to the top of that peak. So in this case, our EAL is much greater, isn't it? And if we have a negative delta H, what kind of process is it? Exothermic. So the products would be lower. Questions?
Delta H
Charles.
is negative.
Oh, sorry.
If
Yes.
Delta H is negative, then it would be exothermic.
Yeah.
That's because it's absorbing energy, right?
No, it's giving off energy.
Oh. That's confusing.
Well, so the energy of the products is less.
Yeah, so you started with more and ended with less.
Right, so that means it had to give off energy in the process. Because it didn't finish with as much as what it started with. Alright, reaction rate.
Oh,
So-
this is my favorite.
This is the rate law. If I say, what is the rate law for this process? This is what I want. The rate law is the whole thing. Rate equals K, concentration of A to a power, concentration of B to a power, etc., etc. That's the rate law. We're going to go through this whole example because it encompasses finding the order of reaction, writing the rate law, and solving for K. So what is the reaction order for each reactant? Put this down. So when we do this this has 3 different reactants. So we have to find, if we're gonna solve for A, we have to find B and C concentrations that are the same with respect to themselves, okay? So this doesn't change, this doesn't change, but these change. So we're gonna use row 1 and 2 to figure out the rate order of A. So A, what happens between the first and the second run?
It doubles.
It doubles, so I can put a 2 here. And it's gonna be to some power. Now, I'm gonna look at the rate. What happens to the rate? It doubles. So, 2 to the what gives you 2? 2 to the 1. So it's what order? For A. First. Alright, now let's do B. We need a B where they're different, but everything else is the same. So these are the same, 1 and 3. Well, 1 and 3 are the same here, so we can use 1 and 3. What happens